So a brief history of X-rays. The thing I should probably say first is we talk a lot about the history of X-rays, and it's a big thing to radiographers. This is a small little chunk of all of the interesting things that were happening in the mid to late 1800s and the early 1900s. There, that roughly that 1800-ish, 1803 is when I'll talk about 1803 in a second, but 1803 all the way to 19, let's call it 27, okay, and maybe even on to the 40s when you consider the atomic bomb. But that 100 and so year span, we learned so very much about how the world works. I mean, we didn't even know what light was before 1800. We knew light existed, but we didn't know what it was, right? We made so much progress in this time frame, and this discovery of X-rays was just one of these little stepping stones along this path to learning all these things. So let me give you a brief history. In the late 1800s, 1895, someone named Wilhelm Conrad Röntgen and other researchers, but he's the main one, were experimenting with a device called a cathode ray. The device is called a Crookes tube or a cathode tube, but it produced a beam of electricity we now know as a stream of electrons. But it produced this beam called a cathode ray, okay? And so basically you hook up these tubes, you see these glass like tube-looking things, these glass light bulb-looking things, and they would hook up electricity to it, run power through it, and it would shoot a little beam of electricity. We now know that's a beam of electrons. They called it a cathode ray because the beam came out of the side of the machine, the side of the thing called the cathode. Okay, there's batteries have like a negative end and a positive end, right? Well, X-ray tubes, X-ray machines, or cathode or Crookes tubes have a negatively charged side and a positively charged side, and when they applied electrical current from one end to the other, the cathode side would shoot out a beam. So they called it a cathode ray. Okay, they called everything rays back then until they learned what they were. We still call them rays. You probably heard about alpha rays, beta rays, X-rays, right? Cathode rays. So yeah, this was the beginnings of us really understanding what electricity was and does. So that's late 1800s. Let me give you a brief walkthrough of how we got to that point. Okay, 1803, the first experiment that showed that light was a wave is done. Okay, now we knew there was light. We knew there was light. We've known about light for quite a while, right? Just look out there and observe that there's light, but we didn't know what light was. I mean, there was ideas that light didn't come from the outside world, that we projected light from our eyes, right? There was ideas that light was a wave or light was a particle. Okay, even Isaac Newton back in the 1600s thought that light was a particle. Okay, so back then, even this hundreds of years before this, they were still arguing about what light was. But it wasn't until 1803 that an experiment was done called the double slit experiment, which I'll actually do for you guys, not today, that shows that light is a wave. Okay, and that was a big deal because we didn't know if light was a bunch of little like if you think about it like a glass of water, right? A glass of water is a bunch of water molecules, right? Presumably you could take one of those molecules and hold it, right? So water is made up of a bunch of pieces, yeah? We didn't know if light was a bunch of pieces or if it was one big continuous blob, one big continuous thing, right, coming at us from the sun and other sources. 1803, we learned light's a wave. That was a huge result, okay? Unfortunately, in the early 1900s, about 100 years later, we also learned that light acts like a particle, too. We'll learn a lot about that, this sort of dual idea, the way that light does both things. But 1803, light's a wave. That was a big result. 1805, we learned that matter was made of atoms. I think we definitely take that for granted now, right? We just know matter's made of atoms. Stuff in the world is made of pieces, right? This tabletop is made of some particle board wood stuff, right? And that's all made of molecules, and those molecules are made of atoms, little individual pieces. Okay. 1805 is when we learned that. The man's name was John Dalton, discovered that the world is made of atoms. Okay. Fast forward a few years, a couple decades, 1839, someone named Michael Faraday learns that electricity, which we knew about, and magnetism, which we knew about, were the same type of thing, electromagnetism, okay? A man named James Clerk Maxwell in 1864 took that idea and demonstrated that electric and magnetic fields were both waves. He made a theory of electromagnetism, a wave theory of electromagnetism. Electromagnetism, by the way, is light. Okay, so they are unifying the ideas of electricity, magnetism, understanding what light is, how it acts, and we're able to write down all these mathematical equations about how light and other phenomenon behave. It was a big deal. They learned that light was just an electromagnetic wave, a wave in the electric and magnetic field that traveled at a constant speed, and that all the phenomenon of magnets, light, electricity were all part of the same thing, electromagnetism. You guys are going to learn about electromagnetism at the very end of this module. Okay, so 1864, we learned that. 1895, we learn about X-rays, okay? So let's move on. So up to this point, up to 1864, we learned about electricity, magnetism. We learned how to control and understand electricity, produce things like cathode rays with electricity. So researchers then learned how to, for interesting reasons, to deflect this cathode beam that they were making so that it exited at like a 90-degree angle out of the machine. Okay, so let me go back to the picture. Any one of these, right? Like let's say this one. The electricity is hooked up to both ends, cathode and anode, negative and positive, and it started off with them just firing the stream of electrons, the cathode ray, from one side to the other inside of this glass bulb. Okay, you had to do it inside of a glass bulb because if it interacts with the air in the room, it would ruin the beam. Okay, so they had to do it inside of this bulb, this thing called a tube. Crookes tube. But shortly after they made these and started to work with them, they were able to take and deflect the stream of electrons so it came out at a 90-degree angle. Okay. Once they learned how to do that, they could start to put material in the way of this stream of electrons and see how the material reacted to this new beam that they were able to make. So they allowed the beam to exit the tube at like a 90-degree angle through a thin aluminum window, and they would place materials with different fluorescent properties in front of the beam. Fluorescence is the property that when a material is struck by some energetic source, it gives off light. Okay, you know fluorescence because you know about like glow-in-the-dark toys and stuff like that, right? The things you have to hold up to light, you turn the lights off in the room and then your little toys glowing in the dark. That's fluorescence or phosphorescence. So they placed these fluorescent materials in the path of the beam to see how the beam affected the materials, okay? At this point in time, we didn't know about X-rays. We didn't know about natural radiation yet. We didn't know about radioactivity or radioactive atoms or any of that stuff yet. So we're still learning. All we knew about was we got some electricity and we can do stuff with it. We can play with it, okay? So they did that. They played with it. They wanted to see how the cathode ray affected different materials, and so they regularly did that. Now the cathode ray, when it was turned on, it was really bright. Okay, and so these fluorescent cards that they were putting in the way and letting the cathode ray hit these cards, sometimes the light coming out of that Crookes tube, that bulb, was so bright that it made it so they couldn't see what was happening to the card. Okay, so they would regularly shield the Crookes tube with black cardboard, and they knew the cathode ray could get through the card. It was like cardstock, right? They knew the cathode ray could get through that cardstock, so they put the black cardstock around it. That way the light from the device didn't interfere with the light that their little cards were making. Okay? Good. That was the first sort of second middle step here. They were able to deflect the cathode beam, and they were able to put cards in the way, shielding the tube from visible light. Now you get to November 8th, 1895. This physicist, Wilhelm Conrad Röntgen, is in Germany in his lab. He's in Würzburg, Germany. Not that we know where that is, but he's in Germany, okay? And he's doing this exact type of experiment. But he happens to notice that a fluorescent card, one of these card stalks that was not in the path of the cathode beam, over here on a bench was glowing while he had his device turned on. I guess no one had done this up to this point, had one of these card stalks, fluorescent cards close enough to the machine but not in the path of the beam. So he notices when his machine's on, this card over here is glowing, okay? The beam's not pointed at the card, so he's going, well, what the heck is going on, right? Up to that point, they knew the cards only glowed when they shot the beam directly at them, okay? Not when they were just somewhere else in the room. this is an accidental discovery that he noticed that there was something when this device was turned on that was making this card light up, that was affecting this card, but there was nothing visible happening between the machine and the card. He couldn't see anything moving between card and Crook's tube. So he goes, there must be something though. Things don't just happen for no reason, right? And he goes, well, I turn the machine off, the card stops lighting up, turn the machine on, the card lights up again, right? And so he's a scientist, he's pretty smart about it, so he starts to do some experiments, and he quickly realizes it just has to be some other form of radiation, some other form of energy that's making this card light up, that's coming from my device, and it's going in all directions. So he takes the card, he puts it in all directions around the room, right? All places around the room, and he notices that it lights up no matter where it is in the room. It has nothing to do with the cathode ray, right? That cathode ray is a beam of energy going to these cards over here, and he can put his fluorescent cards anywhere in the room and they light up, okay? So there's a new type of radiation that we didn't know about before. It was discovered on accident, and he calls it radiation X. Okay, we knew about visible light. We could produce visible light really easily, light bulbs and so forth. And so we learned about a new type of radiation, a type that we cannot see with the naked eye, with the human eye, okay? Couldn't see it, couldn't smell it, couldn't feel it, right? Not detectable with the human senses, right? He calls it radiation X. X is usually used in math when we don't know what something is, like a variable or something, right? It was just a placeholder. For whatever reason, no one came along and fixed it. And it's kind of that way in science. Usually when something gets a name, even if it's a stupid name, the name sticks, right? So X-ray, it's actually kind of a cool name, but it could have been different, right? There was a concerted effort after he discovered them to call them Röntgen rays, okay? Because for his name, right? In fact, even the early field of radiology was called Röntgenology. Okay, because he's the one who pioneers this field. So one of the things he does, for whatever reason, is he decides he's going to put his hand in front of the machine. Okay, so he turns the machine on. So we're not talking about the cathode beam. We don't care about the cathode beam necessarily anymore. He turns the machine on. He puts a piece of cardstock on one side, and he puts his hand in between the machine and the cardstock, that fluorescent material, the fluorescent cards. And he notices that there's a shadow of his hand on the fluorescent card. And not just a shadow of his hand, but a shadow of the bones of his hand, okay? And he goes, that's weird, right? That means that this ray, this new radiation, is not just passing past my hand and absorbing in my hand or passing through it. It's passing through the tissue and getting to the cardstock behind me so that we can see a shadow, not of my hand, but of the bones of my hand, okay? So and this was the first thing he really did. Well, that's weird, right? This thing's obviously able to pass through my hand and get to the cardstock behind my hand. So in a series of brilliant experiments, he does more, and he's able to determine with his experiments that X-rays, this new ray, travels in a straight line. That's a big deal because visible light bends, right? If you try to look through, I'm gonna borrow Lewis's bottle. If you look through this at me, right, you can't see straight at me, right? Because light going through this medium, through that water, is bending, is refracting as it goes through the water, right? If you ever stand at the edge of a swimming pool or a creek or any clear body of water, what you can see is not along that path. It's usually straight down from that path because light is bending as it travels through the water, right? You can't see directly through water because it refracts light, okay? Light bends. Visible light bends. X-rays don't bend. X-rays only travel in straight lines. They do not refract or reflect. You cannot use X-rays to see yourself in a mirror, okay, because they don't reflect or refract. So they travel in straight lines. That was a big deal. His next thing that he learns is X-rays are stopped by lead. He was able to put lead in the way of the X-ray beam, and now his little card stalks don't light up, okay? So he's trying to figure out, like, he realized it can travel through my hand. He obviously knows it can travel through, like, cardboard because the device was shielded with cardboard the whole time, okay? So it travels through some materials, cardboard, human body tissue, right? But then he's like, all right, well, what will stop this stuff, right? So then the heaviest thing he's got is lead, so he puts lead in the way, and yeah, lead stops it, okay? That's why we use lead equivalent nowadays. and it casts a partial shadow from most other objects, hands and other things, okay? So he learns X-rays travel in straight lines, stop by lead, and they cast partial shadows of things. His next experiment was the big deal, okay? His next experiment was, for whatever reason, he doesn't use his own hand. He calls his wife in, okay? And remember, they don't know that X-rays are dangerous yet, okay? The field of radiography is born when, after seeing the image of his hand, his waving his hand in front of the cardstock, like I said, he goes and gets his wife and gets a piece of photographic film, puts it in a film jacket, and puts her hand on top of it, puts the machine above her hand, and takes a 4-minute exposure. Turns the machine on for 4 minutes, and then she moves after that, and he develops the film. This is the first radiograph ever taken, okay? And you can pretty clearly, sorry, let me try to center it.
Alex,
You can, yeah.
You mean when he shoots the X-ray, it's like 4 minutes?
Mhm.
Like, really?
Hey, it just turns the beam on for 4 minutes. You guys know you make exposures for like milliseconds, right?
Yeah.
He turns it on for 4 minutes.
I really
She's a
forgot
good
that. I'm like,
But a couple things to remember. There was no such thing as intensifying screens inside of cassettes at that time, so the exposure would have had to last for a long time to even make an exposure. There was no shielding also in the X-ray tube, so there's no filtration in the X-ray. So no shielding, that's one, but no filtration in the tube. So like all of those low energy X-rays were just absorbing right into her body. Okay, so no filtration, no intensifying screens. For lots of different reasons, it had to be a long exposure. But yeah, he makes a 4-minute exposure, so she has to sit still for 4 minutes while the machine's on and going. But it worked. He develops the film, and oh my gosh, there's a picture of her bones of her hand on that film. Okay, and this is her. Okay, you can even see her wedding ring. Okay, that's that right on the ring finger, right? That's that big bright circle. So there you go for our first X-ray taken. We actually have the magazine article that this was in our back hallway of the school. You can see it if you walk down to like financial aid or something. You'll see it on the wall. But there you go. That's the big discovery. This sparks the whole field of radiography. Once a scientist named Röntgen realizes, oh my gosh, you can take pictures of people's bones with this new thing that I created. Okay, and boom, it was off and running. Remember, November 8th, 1895. That's the end of the year in 1895, right? By like summer 1896, we've got X-ray machines in hospitals. Okay, like that quickly, a year, and that in the United States, right? So that he was in Germany, we go all the way to the United States. We've got X-ray machines happening in 1896. Okay, so let me give you a little bit more context to this. That was the end of 1895. Huge deal. He gets Nobel Prize for that. Okay, not in 1895, but the next Nobel Prize, he gets a Nobel Prize for it. Okay, 1896. Henri Becquerel, which the name Becquerel should be familiar to you. What is Becquerel associated with? It's a measure of radioactivity. Like it's a unit of radioactivity. A certain amount of becquerels is a certain amount of radiation. Okay. We use that name, that term Becquerel because of this person, Henri Becquerel. 1896 discovers natural radioactivity. So to be clear, what Röntgen did was to discover man-made radiation, right? You need to have a device, needs to be able to turn on, hook up to electricity. That's man-made, right? We discovered man-made radiation. It's kind of odd and a historical interesting fact that we discovered natural radiation, the kind that's just like out there in the world doing its thing all the time and has been since forever. We discovered that a year later, right? So for whatever reason, we discovered the natural stuff after, which really should have been the first thing to be discovered. But this was another accident, okay? Sometimes in science, accidents happen and they're good accidents, right? So this person, Henri Becquerel, was studying phosphorescence. These are materials like a fluorescent material, but that continue to glow after you remove the energetic source from them. Like the glow-in-the-dark toys we have. You turn the lights off and they continue to glow for a while, right? That's phosphorescence. Anyways, he's experimenting with these. He has them out in the sun. And for whatever reason, he takes his material, and it's a cloudy day. He's frustrated. He can't do his thing. Not enough sunlight. So he places, and what they would do was they would take this phosphorescent material, expose it to sunlight, and then put a photographic plate near it. and then they would let the material just emit light and expose the photographic plate. And later on, they would process the plate and see how much exposure the plate received and infer from that how much light the little material emitted, okay? That was the way that they tested phosphorescence. Anyways, so he places the wrapped up photographic plate with the material next to and in a drawer by this crystal he has, okay? He doesn't know it, but this crystal's radioactive, okay? And his plate, his photographic film he was going to use was unused for that day. He didn't go out in the sun, didn't use his photographic film, sticks it in a drawer next to this crystal. Later, for whatever reason, maybe he pulls the plate out, doesn't know if it's been exposed to light or not, so he just goes ahead and processes it. He goes ahead and develops the film, okay? He notices that film was fogged. The film had gotten exposure, but it was in a drawer, not being exposed to light, covered. The only anything else nearby was that crystal. So presumably he does this more than once, because usually you try to double check things. But anyways, he concludes that some new type of ray, like Röntgen's rays, were being emitted from that crystal. That's the only explanation for why this photographic film was being exposed to something while it was in that drawer. He called it X-rays. He said X-rays were being continuously emitted from the crystal. He doesn't know it yet, but what he has found is that he has a radioactive material that's emitting radioactive particles, that's emitting particles of radiation. These particles are called alpha, beta, and gamma rays, or gamma particles. We call them rays or particles, doesn't matter. He thought they were X-rays because he didn't know about natural radiation. It took a while after his discovery for us to realize that they were alpha, beta, gamma rays. And it's not X-rays, natural radiation. Okay, this is a year after Röntgen. Becquerel discovers natural radiation. So naturally, both Röntgen and Becquerel get Nobel Prizes. When you learn something about the world that's a big thing, you usually get some sort of reward from it, and in this case, a Nobel Prize in physics. Röntgen's work begins a revolution in physics that includes understanding the nature of the atom. We learn a lot about how atoms work shortly after Röntgen does his thing. In experiments in the early 1900s, Ernest Rutherford finds that alpha particles were what were being emitted from Becquerel's material, and they were a helium nucleus. You guys know what helium is, right? We use helium in balloons and stuff. Alpha particles were equivalent to a nucleus of helium. They're big things. Rutherford then goes to prove the existence of this thing called the proton, which we now know is the main charged particle in the nucleus of atoms. Okay, he discovers the proton. He predicts the discovery of the neutron, and interestingly, one of his students discovers the electron. So, and I think another student after him discovers the neutron, but he predicts that they're there. So we learn the three important elementary particles for atoms: protons, neutrons, and electrons, because of the stuff that Röntgen and Becquerel did. Okay, so these first experiments give us the starting points to learn these next things. Now, Rutherford did his own experiments with his own devices and his own equipment, but he's the one who gets us to the level of understanding what atoms look like and are built like. He also gets a Nobel Prize. So that's the end of that short story of the history of X-rays, and we finish with this picture. The first X-ray unit, which this is a picture of, is installed at Massachusetts General Hospital in the United States in 1896. This is what I was saying. So we got taking X-rays of people a year after, not even a year after, because we're talking about the end of 1895 was the discovery. Now, they did things like put a lead cone that would be used to kind of guide the X-rays. We would call this nowadays a collimator. Okay, I think in fact they probably used that same term back then. But if I zoom in on here, if you took radiation safety with me, you know a couple things. So what are you seeing that's not safe, that we would not be considering safe nowadays? So it's very close, right? So that thing that's up there above the cone, right, is the X-ray tube, or the Crookes tube still at that point. It's very close to him. What do we know about proximity, distance from a source of radiation? How does distance affect exposure? There's a law, that
Inverse square.
the inverse square law. So tell me something, Lewis, about the inverse square law.
Like it's like the further you get from it, the beam is cut by it's exponentially cut.
Yeah, there's an exponential like decrease in exposure as you move away, right? So as you move a source of radiation close to someone, their exposure goes up, right? And not by a little, but by a lot, exponentially higher. Okay, we know exponents make big numbers, right? So exponentially higher. I won't go over the inverse square law in its actual form right now, so don't worry. But so the X-ray tube is very close. Okay, so that's one thing. He's very close. That's probably not a safe thing. Is there any other things from a radiation safety standpoint that you see maybe not being done well here?
Cover his gonads.
Then it's not covering his gonads, right? There's no gonadal shielding because we don't know about harmful radiation yet. We don't know that these radiations are harmful. Do you guys remember what year the first person dies from radiation exposure? 1904. Okay, this is 1896. So we still have 8 years to go until we learn about the first person dying. That person's name was Clarence Daly, and he's the first death from radiation exposure. And it's 1904, and he is Thomas Edison's personal assistant. Okay, Thomas Edison, who is in the United States, gets a hold of Röntgen's information and builds his own X-ray machines like right away. Okay, Thomas Edison invents something called the fluoroscope, the video X-ray machine, right? And that's in 1896 he does that. And so his assistant dies 8 years later from X-ray exposure.
Hand, right?
Yeah, the guy who lost his hands. Yeah, because hands are so easy to put in the way of the beam, so people keep putting their hands in the way. And yeah, Clarence Daly loses his hands almost entirely by the time he dies. All right, so the X-ray machine's very close. There's no shielding for this person's gonads. The X-ray machine itself is not shielded, right? It's just a glass tube right there, right? There is nothing stopping those X-rays from going all over the room, okay? So there's a number of things from a radiation safety standpoint that are being done wrong here, but you can't fault them for doing them wrong because they don't know better yet, right? We only know better now because lots of people died because of doing things like this, okay? And there's other things too, probably the film they're using back here, it's going to require really long exposure times. He's got to keep still for very long, but it's huge, right? Think about prior to the discovery of X-rays, prior to 1895 and Röntgen's picture of his wife's hand. How do we see inside of people's bodies? You cut them open, right? Or you don't see inside, right? You don't see what's going on. So there's surgery to open body parts up, but the rest of everything is done. Think about people have been breaking bones since there's been people, right? Literally, the first evidence of civilization that we have is from a healed femur, right? A healed femur of somebody who broke their femur and didn't die. They were kept safe and were able to heal. That's huge evidence of civilization. That's the first evidence of real civilization. So we've been breaking bones and healing them since forever, okay? We didn't get to see bones without surgical intervention until 1895, okay? So prior to this, how do doctors tell that you have a broken bone? They either see an obvious deformity, right? Or they go in and they start manipulating you around, start moving those pieces around, feeling your broken bones moving, right? And we're talking like pre-anesthetic too, right? So this is a pretty crude science. Medicine's pretty crude, right? And it still is, but it was very crude in the way it was done. This was a huge, huge change in the way we do medicine. Now with like zero intervention into the body, we can now see inside the body and see what's going on, get a look at the bones and the joints, see how they're interacting. So this was a really, really big deal. And obviously it's still a big deal because we're still very important in the field of medicine. Everywhere that you go, it's going to need radiographers, right? X-ray techs, right? Everyone needs ability to take X-rays. Huh? Every day. Okay, good. So let's talk now about how it develops from the first X-ray tubes in Massachusetts General Hospital in 1896 all the way to what we have nowadays, right? Because obviously the stuff we have nowadays is much, much different. But interestingly, like the principles are still the same. The principles are still produce a high energy beam of electrons called a cathode ray. That cathode ray smashes into something and boom, X-rays are emitted from that source, right? That's what we do. We still do the same thing, just with better equipment nowadays. Okay, So the history. You learned 1896 was the first X-ray machine in the United States. Edison invents the first fluoroscope. Fluoroscope sort of means like light up camera, but the idea is, so let me zoom in on here. Well, let me read first, and then I'll zoom in on the picture and talk. So Edison invents the first fluoroscope in 1896. So again, less than a year after Röntgen's discovery, right? Word travels fast, even back then. This consisted of a fluorescent screen at the end of a light, tight viewing cone made of metal. And in a box underneath that person's hand, which that person is Clarence Daly, is an X-ray tube inside of that wooden box. Okay, so let's zoom in on here. So the person looking in through that viewfinder with his hand in his pocket, that's Thomas Edison. The person sitting sort of back with his hand on the box, that's Clarence Daly. Okay, and the X-ray machine is in that wooden box that the hand is on top of. Okay, so X-rays are emitted in all directions equally in all directions from that box. So some of them go up through the hand. Okay, they go up through the hand, and Edison's looking down on the fluoroscope. Now that fluoroscope is kind of like those fluorescent cards that we were talking about at the very beginning. Okay, so as long as that X-ray tube is turned on, you have Daly's hand right here. Edison can look in through that viewing cone and see in a outline, see a shadow of the bones of Daly's hand. Okay, so he can see the bones, he can see the joints between the bones, he can watch Daly move his hand, and as long as the machine's turned on, he can see Daly moving his hand and watch in real time those bones moving. Okay, this is a fluoroscope. This was a big, big deal. So we had plain film X-ray this same year being created, but Edison goes one step further to make this thing called the fluoroscope in that same year. So not only can we take plain film like still image X-rays like we have nowadays, but we can also take, not take and record, but we can perform these moving dynamic studies. The only problem with them is that we couldn't make a recording of them, right? Once it's turned off, all the information's gone, you just have what you remember, okay? Whereas the plain film, at least you had a record, right? But a fluoroscope was a big deal. Let's briefly discuss from a radiation safety standpoint, maybe some things that we noticed that are not great happening here. So let's talk about the box, right? Does dry wood measurably stop X-rays? No, right? What stops X-rays? Lead, right? Enough dry wood might have, but you need a lot of it. You need so much of it that it would just be this big cumbersome mess, right? So you need something like lead to stop X-rays. So those X-rays aren't being stopped. In relationship to where the box is, where are the gonads of these two guys? Right underneath and right next to, right? So very close, okay? They don't know they're doing something wrong. How about relationship of the rest of their body to the X-ray tube? Very close, right? Because, you know, to view through the view box, you got to be right up on top of the person, right? And the person's got to be right there too, right? There's no shielding aside from that dry wood, which is not a good shield. And the other thing is that the device has to be turned on and left on like a light bulb in order to work, right? As long as it's turned on, it's emitting X-rays, so you can see things as long as it's turned on. But as soon as it's turned off, all that extra information's gone. So there you go. So from a radiation safety standpoint, not great, but again, we don't know, right? That guy with his hand on the box dies 8 years later, and then we learn, okay, shortly after that. Now, interestingly, I believe it was like 1899, we had our first recommendations for reducing radiation exposure by someone named William Rollins. He's a dentist. But we don't really put any of this into practice for years and years and years. Okay. But, you know, from 1896, fast forward about 50 years, the state of the art is fluoroscopy. Okay? So this is your, at that time, a modern day radiologist. Okay? So this is all the way up until the 50s. This was what radiology looked like. Okay? You had a doctor, radiologist. They were doctors. There was no radiologist before X-rays were invented, right? So X-rays get invented, you get doctors who are like, oh, that's really cool. I want to do that, right? I want to be the person who is specializing in the use of radiation to cure and treat people, right? They call themselves radiologists. So you have a radiologist. You have, and I know this is a blurry image because these are obviously from the early 1900s. You've got a screen. This is your fluorescent screen. So Edison had that view box, right? His little fluorescent screen was in the view box. They took away the view box and made a big giant screen because so you can see things more than just hand size. And you have this fluorescent screen. Have you ever seen like the old Looney Tunes, like Bugs Bunny or whatever, will pull that rolling screen in front of him or someone else, you can see like an outline of a skeleton. That's what this is from, right? They're making a joke about the fluoroscopes. But that's what it is. It's a big rolling screen thing that lights up and fluoresces when exposed to x-rays, okay? So you put that on one side of the patient. You have to put the patient very close to it, okay? But then you have a patient, all right? So there's your patient being treated or being done, an exam being done. They're trying to look somewhere at the chest or abdomen of this person. And then right here, you have the x-ray tube, okay? Again, that's just a Crookes tube. So it's an unshielded, open x-ray tube that emits a cathode ray and shoots x-rays in all directions, okay? And that, again, has to be very close to the patient. The other thing that they need to do here is they need to turn the lights completely off in the room. So radiologists had to learn that these screens didn't get very bright, so they had to have all the lights off in the room so that they could dark adapt their eyes to what they were seeing, which is kind of why we still continue that nowadays. You notice in our x-ray rooms, at least where the viewing areas are, very dark, right? Helps us with from distracting lighting. If you ever go into a radiologist's office with their multiple screens, they will have the lights completely down in the room. They might have some backlighting somewhere, but the lights will be down so that they can have their eyes dark adapted to it. So that was the deal. Radiologists dark adapted their eyes to view the fluorescent screen suspended over or next to the patient. Very high technical factors had to be used. So large amounts of radiation being produced. Patient doses were very high. The way we make an image darker is to increase the amount of x-rays being produced, right? Back then, the way to make the image, for fluoroscopy, brighter is better. Okay, for this type of screen, fluorescent screen fluoroscopy, the brighter the image is, the better, which is equivalent to our images being darker on our screens. But anyways, they had to use high amounts of radiation to make the images bright enough to see. Okay, and so large patient doses, high exposure to the patients and the radiologists. Okay. It was because of this technique of being very close to the patient and the source of radiation that radiologists were found to be dying earlier than other doctors. They were having shorter lifespans than other physicians. We learned about that in radiation safety, how early on the radiologists were having shorter lifespans. Lifespan shortening is a risk of radiation exposure. Nowadays, it's not a risk anymore because we're safe with our radiation. All right, so we advance from there. You get to 1948. This is not an image from 1948, but you get to 1948 and a device called an electronic image intensifier is invented. By far, the highest exposures in radiography came from fluoroscopy. Okay, that screen thing that I just showed you, plain film like diagnostic x-rays do not, even if the exposures were for a minute or two, they did not make for very high exposures to the patients. Okay, it was easier to expose the photographic film with low amounts of radiation. But in fluoroscopy, what I just showed on that last slide, they had to use large amounts of radiation. So you get to 1948, we invent something called an image intensifier. It basically replaces that stupid fluorescent screen, okay? And now you've got a better way of making and viewing your images electronically, and that lowers patient dose to 1/100th of the previous levels, 100 times less, okay, just by inventing this new device. That's a big deal. This is what you're seeing here on this picture is a modern fluoroscopy machine. That thing that they're pointing to is the image intensifier. That is not the x-ray tube. The x-ray tube in a fluoroscope is underneath the table. So that is what, Edison was looking through that little cone thing, right? This is the electronic equivalent to that. Okay, it makes the patient doses much lower and works a lot better. All right, so that's our brief history of some of the discoveries. Let's go to some more developments in modern tech. So this will actually backtrack just a little bit. We backtrack to 1899. So for reference, this is 4 years-ish after Röntgen, okay? Dentists begin very quickly to realize that they can use this, right? Because teeth are bones, right? Teeth are like bones, and we can use this to see the teeth, just like we can see other bones, right? So dentists really like the plain film part of this, okay? William Rawlins, a dentist, in 1899 develops the first, he calls it an aperture diaphragm, but it's a collimator. Okay, he develops the first way to control and cone down the X-ray beam, to control the X-ray beam. That's huge, right? Now you can actually adjust the beam to be a different size and not just be everywhere, okay? And he develops the first X-ray beam filters. So we learn that there are low energy X-rays that we don't necessarily want, and we filter them out. We pass those X-rays through a sheet of aluminum. Okay, we still do that nowadays. Okay, that's 1899. So he's pretty early on, right? This is before the first death. He's just trying to make better equipment. Okay, and he's also the first one to propose radiation safety guidelines. His guidelines weren't very great. He said something like, you should, expose yourself to less radiation than would fog a piece of film in a 24-hour period. So it's a lot of radiation. It was like 100 millirem or something like that. But he made the first recommendation, right? That's a big thing because he's the first person to say, hey guys, we should probably not be exposing ourselves to so much of this stuff. Let's reduce it, right? So he keeps a piece of photographic film with him, and at the end of each day of work, he goes, all right, is my film fogged? And if it is fogged from exposure, the next day he goes to work, he tries to reduce his exposure. That was the first way of being safe around radiation. You get to 1913. We've had this stuff for, a few years now, decade and a half. Gustav Bucky, that name should be kind of familiar to you, Bucky, introduces the first grid for reducing scattered radiation. He's the first person to say, we should probably do something to improve image detail. We want to make our images better. I noticed that when we take images of large body parts, they're kind of, low contrast. They're not very good quality images. Let's develop something to make these images better. We call it a grid nowadays. They even called it a grid back then. And he invents that in 1913. And in 1921, someone named Hollis Potter connects his grid, Bucky's grid, to something called an oscillating diaphragm, I think he called it, or an oscillating mechanism. Basically, he makes a grid that shakes, okay? What happens to think photography, of taking pictures of just the world. What happens to something when you try to take a picture of it and it's moving very fast?
Blur.
And what happens to stationary things? Clear, right? So if you take a picture, like if you're stationary on the road and you take a picture and there's like mountains in the background and then there's cars zooming by you, the cars are usually blurry, right? And the mountains in the background very clear, yeah? The grid would be like the cars, right? We don't want to see the grid, okay? We want to see the mountains in the background, right? The body part, right? So you shake the grid during the exposure and it blurs it out, but you still see the body part because the body part's not moving, okay? That's our modern day Bucky grids do that. They oscillate. They shake during the exposure so that you don't see them. Has anybody ever used a stationary grid, the kind that goes on the tabletops on top of your cassettes? No, we have them here, so you'll use them here. But so you stick the cassette in the tabletop, right? Or sorry, not tabletop, but in the Bucky tray. On top of that Bucky tray, there's a Bucky grid, okay? And every time you make an exposure, that Bucky grid shimmies a little bit, and it shakes and blurs out the grid, so you don't see the vertical grid lines, okay? If you use a stationary grid, you will see vertical grid lines, because what a grid is a series of upright lead strips that are very close together that sit underneath the patient and above the image receptor, and they catch the scattered radiation that's traveling at weird angles. The grid strips actually catch and catch the X-rays to keep them from hitting the image receptor. If you can shake the grid during the exposure, it just blurs the grid out. Still functions well to reduce scatter, but it's not visible. 1921, Hollis Potter makes a grid that shakes. That was nice. It improved the images better. Unfortunately, when you're the first person to discover something or to make something, you usually get your name attached to it. When you're the second person to advance or make it something better, you usually don't get your name attached to it. So we call these things Bucky grids, not Bucky Potter grids, right? And that's why we call these a Bucky nowadays. Okay, so that, to be clear, if you haven't seen this before, underneath the table, in every X-ray table, there's this tray. This is a Bucky tray, okay, right? And when you put this tray back into the table, you can't see it, but above that tray, there's a grid, okay? The grid is there to stop scattered X-rays as the X-rays come down through the patient and get to the image receptor that's on that tray, okay? The grid helps make our images better.
I shot a pelvis the other day,
Mm-hmm.
and you know how sometimes you're going fast, like boom, boom. So I thought I lined it up with the bucket.
Yeah.
Over here, I shot it. I was like,
And no
"I still
exposure,
got
right?
It still got it." And then the instructor was like, "What? Why?" And she moved the bucket. The bucket was over here. I was like, "Oh, it still came out though."
How did you get an
And
image?
she didn't know too. It was over here, and it was lined up. I was like, "Okay, I got this." And shot it.
Okay.
She's like, "That's bad."
Yeah. So that's a big thing, right? Making sure all three things are lined up:
Yeah.
X-ray tube, patient, and image receptor, right? That last one, the image receptor, is easy to forget.
But it's the fact that there was like a lot of patients that morning.
Yeah,
It was
you're
crammed
moving
up,
fast.
and
Yeah.
Now you got to pick up the speed.
Yeah, and then like you're trying to move fast, but then moving fast ended up making you have to go back
Oh, I
and do
was
it
making a
again.
mistake. Little by
Right?
little it was creeping. I was like,
I bet you if you just moved at a nice consistent pace, right?
Yeah.
Spent enough time on each thing so you don't make a mistake, you'll
Right.
probably get things done quicker than if you try to speed up.
and at the urgent care, that side became much more better. But at the orthopedic office, it's like you see him 30 within like 3
Yep.
hours.
So it's a stupid philosophy that I have, but slow is smooth, smooth is fast. Okay, if you're going slow, you're going smooth. If you're going smooth, you're going fast. So if you're going slow, you're going fast. It's goofy, but it works, right? If you think in that way, you will, and you've got to think systematically too, right? But I've been there with what you're saying. I've been crammed, jammed for time, and
Yeah.
it's hard, right? You're trying to move patients, and you got doctors waiting on X-rays, and it is difficult. Yeah, slow is smooth, smooth is fast. Okay, good. That's you guys will all have stories like that where you made goofy mistakes and you're not going to forget it again. Oh, you might, but you probably are not going to forget it again, right? You make those goofy mistakes and you don't forget them. I still remember the times when I, as a student, forgot to turn automatic exposure control on at the table and left it turned on at the wall, and my patient's on the table, right? And then the wall's waiting for exposure, so it never turns off, right? It hits the backup timer for the exposure. So I gave the patient, 400 times the amount of exposure they're supposed to receive, right? Those mistakes happen, and you don't do them again, right? I will never forget that. Okay. I was like, I literally I'm like, what are my images? Not what's happening. And so I called the X-ray tech over, and of course, immediately a trained X-ray tech is going to go, well, which Bucky did you turn on, right? And he says the wall is turned on when I'm here at the table. So I'll never forget that, and you guys are going to make your own mistakes. And
So like whenever you're doing whenever you're using the bucket, you can actually see like.
no, you can't see it or hear it. It's pretty quiet and pretty minor, but it does actually shake. So that Bucky grid actually oscillates. That's why, among other things, that's why you have power going to your table, right? So part of the power going to your table is like to move the table up and down, and move, but part of the power goes to the Bucky grid and shakes it every time the exposure turns on. Yeah. So that's your table's actually connected to your exposure timer because of that. Yeah. So it shakes during the exposure. Yeah, you'll also know if you at your control console don't have the control console turned on to the table Bucky, but you shoot in the table Bucky, you will get your grid not moving. Your grid will stay stationary, and you will actually see grid lines on your X-ray. Yeah, you have to turn on either wall Bucky or table Bucky, right? So when you're telling, you guys who know this, who you're at there, you have to tell on your control console, have to press wall, table, or tabletop, right, or none.
Yeah.
You're doing that because you're turning on the Bucky in the table or at the wall, or turning both of them off if you're doing tabletop. So yeah, if you shoot X-rays on the tabletop in the Bucky tray, but have the wall Bucky turned on, not the table Bucky, the table Bucky's grid does not shake during the exposure, and you're going to see grid lines, these white lines on your image. And what's really nice though is there is software in our computers that can actually take those away in some circumstances. But you want to start off by doing things correctly and turning on the correct Bucky. That's why you select wall, table, or none when you do that. You're turning on the right Bucky. Okay, let's fast forward now from 1913 with Gustav Bucky to 1942. 1942, not too big of a deal here with the name. You're not going to have to remember this name too much, but Russell Morgan is the name, and you get the introduction to something called a phototimer. Phototimer, or AEC, which also stands for Automated Exposure Control, is a way of not having to set your technical factors, not having to set an amount of radiation. The machine sets the amount of radiation during the exposure. It shuts off the exposure when the detector receives the right amount. That's great, right? Because now, for a thick patient or a thin patient, you don't have to decide how much exposure to give them. The device can do it in real time, okay? There are disadvantages to this photo timing. Who uses AEC? Are there some disadvantages that you've seen?
There wasn't much yet, but just a lot.
How about for positioning?
Positioning?
Do you have to be really accurate with your positioning?
Oh, yeah.
Yeah,
Oh, yeah.
that's the biggest thing about
When you
AEC.
shoot it, like, oh, you
Yeah.
missed.
Yeah, AEC relies on these detecting chambers at the Bucky, right? And if you misposition your patient so they're not on top of the detecting chamber, the exposure will either shut off too soon or too late, making the image over or underexposed. So you have to be super accurate with your positioning. But they're great. They're a tool, another tool for us, right?
Yeah.
Okay, we're backtracking now, back to 1913, okay? 1913, we develop the hot filament thermionic emission X-ray tube. This is an advance on the cathode ray tube. So now we don't use Crookes tubes anymore.
Was that the thing that makes the room all hot?
No, well, no, so I mean, you're making heat anyways, right? Even if it's the Crookes tube, right? The rooms get warm though, right?
Oh, yeah,
Machines
they
produce
do.
a lot of heat. So on this one, in image A, is the thermionic emission tube, and it's just a difference in how the X-rays are produced. You see a small little gap in the middle of that tube between those two things, right? The X-rays are produced from the one on the bottom. Sorry, the stream of electrons is produced from the thing on the bottom called the cathode with a filament. A filament is like coil of wire, like a light bulb, and the cathode ray, the cathode beam, flies across and strikes this target. Okay, when it hits this target, X-rays are produced in all directions. It is a more efficient way of producing X-rays than the Crookes tubes. The Crookes tubes made X-rays, but they didn't make them in a very efficient way, in a very controlled way. This allowed us to have more efficiency, more control.
It actually has like light bulb threads.
Yeah, absolutely. I have pictures that I'll show you, but yeah, they even inside of your modern X-ray tubes, which is so 1929, you get the first what's called a rotating anode. The opposite side of the cathode is the anode. Okay, so on the one on the left, the thing on the bottom is the cathode. The thing on the top is the anode. On the right, you get the first device that has a spinning anode. Okay. The only reason for the anode side to spin is to dissipate heat, to be more heat efficient, okay? So it's just a more efficient way of doing this. In fact, dental X-ray tubes don't have spinning anodes. Even modern dental X-ray tubes do not have a spinning anode. You notice when you get a dental X-ray, the machine just makes a beep and then it's over. You don't hear the machine making a bunch of noise, right? But when we make our exposures, our machine has to like make a bunch of noise for a second and then we can make an exposure. All that noise is from spinning the anode, and it's the mechanical noise of the bearings rubbing on metal and stuff, making noise. But it was a way of making the X-ray beam more efficient and with better heat dissipation. So that's the rotating anode tube over here. But yeah, so back to sort of what Lewis was talking about. This side, this cathode side, has in it a coil of wire. In fact, these modern ones have two coils of wire, but it's exactly like light bulbs. So if you ever held a light bulb, not the new LED bulbs, but the old incandescent light bulbs, right? They have a wire running up into the bulb, coils across, right, and down the other side, yeah? And if you look at them close when they're turned on, be very careful, but if you look at them close, you notice that the thing that's producing light is that coil of wire, right? That coil of wire is getting very bright because it's getting very hot, okay? That's what's happening here, okay? We run electricity through these coils of wire and we heat them up so much that the electrons in the wire, they jump off of the wire. They hop off. We call this thermionic emission. In an upcoming module, equipment operation, when we get back to it, you'll be out of there by that time, but that's when you came in equipment operation, right? So maybe the first things you learned were how X-rays were produced and what the X-ray tubes were made of, right? It's tough stuff. But you know, we learn about thermionic emission. We learn about making the X-rays by passing a lot of electricity through that small coil of wire, boiling the electrons off into the space around the wire. Thermionic emission. So this was a huge, huge improvement in the equipment, and we still use these technologies today. Okay. Let me move forward a little bit. So we fast forward now a little while. We get to the 70s now, okay? After nearly 80 years, the development of intensifying screens, which made rare earth compounds, reducing patient doses to half of the previous levels. Intensifying screens are something that, let me pull out this cassette here. Nope, not that cassette. Let me see, do I have a cassette in here? So let me first show this, and then, yeah, I'll be right back, actually, 2 seconds.
You guys can have a long weekend this week, it'd be nice.
Well, I didn't see him like 78 patients.
Oh, I know, yesterday was good. It was crazy.
I'm trying to do everything at the same time.
At the same time, yeah. But you're doing more medical assistance because they're paying you, yeah.
I just got my bone.
Okay. So let's in our heads sort of rewind back to Röntgen's time. You know that photographic film is light sensitive, right? If you open up a film camera, you know, before the film's wound back into its little capsule, right, the film gets ruined, right? So photographic film is light sensitive. X-ray film, the fact that we used to use things we used to use before digital, it's light sensitive too. Okay, so to like change out film inside of a cassette, you have to be in the dark room, right? The first thing that they invented to do this were these cardboard cassettes, okay? Basically, they were just pieces of thick cardstock or cardboard that inside of them you could place a piece of photographic film in here, okay? Seal up the edges so that it's sort of light tight on the edges, okay? Wrap these little edges around the film, and you close this thing up, okay? And now you've got a cardboard cassette. The film is in here, and what exposes this film?
The light from the X-ray.
Right, so the X-rays expose the film, right? And for X-rays to expose the film, you needed a lot of X-rays. I mean, long exposure times, high technique, okay? What you can do instead, what Edison and others figured out, is that instead of a piece of cardboard, well, even if you were using cardboard, you can take and line the inside of the cardboard with something that is fluorescent, okay? So what exposes photographic film in cameras, like regular cameras? Light, right? And we were using photographic film, and we were exposing the film by exposing it to X-rays. But the film could also be exposed by light, yeah? So what you do is, you take and line the inside of your cardboard cassettes, or the modern day plastic cassettes, with these things called intensifying screens. These intensifying screens are made of material that lights up when exposed to X-rays, okay? So you take your film, you put it in here, notice there's an intensifying screen, these white screens on both sides, okay? And you close it up. Now, when you make the exposure, X-rays pass through the body part, and instead of the X-rays exposing the film, the X-rays strike the intensifying screens. The intensifying screens fluoresce, they light up, and the intensifying screens expose the photographic film. This lowers patient doses to less than half of what they were, okay? The first intensifying screens lowered doses to about a 50th of what they used to be, and then we cut it by another 50% when we get the better intensifying screens in the 70s. Intensifying screens had been invented in a lot earlier, in the early 1900s, by Edison, but they got made better in the 70s. Okay, one of these times I'll give it, because we only use digital now, so we don't really get to see this anymore. But one of these times I'll take you into the X-ray room. We'll open this up and expose this to the X-ray beam, and you can see this plate lights up. It's either green or blue. It's kind of cool. You have to be in a really dark room for it to work. So we'll turn the lights off. We'll make an X-ray exposure. You'll see it work. But yeah, this is an intensifying screen. All cassettes that are film use intensifying screens. It basically is a way of lowering the patient dose by letting the screen do the exposing of the film rather than the X-rays. The X-rays do some of it still, but a lot of the hard work is being done by that intensifying screen. Okay. Also in the 70s, you get the first computer processing of static images. You get the first digital images. We called these first digital images computed radiography, or CR, which is, we still call it CR nowadays. CR is the type of radiography where you take the image, the cassette still has to go to a processor, but there's no photographic film anymore. And your images are displayed as soft copy on the computer screen. To also give you some context here, 1966 is the invention of sonography. So X-rays have been around for a lot longer, but digital X-rays were invented after sonography, after ultrasound. And CT and MRI get invented right about the same time as digital X-ray. All these inventions helped each other along the way, so they all get invented right about the same time. CT is computed tomography. So instead of computed radiography, you have computed tomography. A tomogram is a cross-sectional image of the body where radiographs are sort of three-dimensional compressed images, right? Tomograms are cross-sections. MRI, magnetic resonance imaging. MRI uses magnetic fields and to manipulate your electrons and build images of the body in that way without any radiation, which is really cool. What I'd like to do now, what are we at right now? Almost 11? Yeah, let's take our break right now. Let's take our 5 to 10 minute break. That actually is a perfect point to stop and